I think I am recording. Yes, I'm recording. Okay. Let's go a little bit louder here. I think my battery's running out. Okay. First of all, take a look at the chain rule in your notes. Okay, we're going to take a look at the chain rule today, section 2.6. You've already studied about composed functions. Composition of functions, a very important concept in mathematics. It can be expressed as f of g, or quite simply f o g, or for those that really like descriptive, fog of x equals f of g of x. So it's a nested function. G of x is nested inside of f of x. This often happens in mathematics. So we have, of course, a way of doing this derivative. We start at the outside. We take the derivative of the outside function first. So start with the derivative of f of g of x. Then we follow it by the derivative of the inside function. All right, so outside function, inside function, g prime of x. We have to apologize to a famous mathematician for misspelling his name here. There's no T right here. So Leibniz, no T in his last name. So if you wouldn't mind crossing that off. All right, so Leibniz came up with the denotation for derivatives. That's his favorite way of saying these. If we use the Leibniz rotation, we redefine the inner function as u. And u is the favorite substitution function letter that we're going to use all the way through the course. So u will stand for the inner function quite often. So the way this works is we take the derivative of y with respect to u and follow it with the derivative of u with respect to x. Now, your teacher has this on here, which is correct. This is easy to remember because if dy over dx and du over dx were fractions, the du's would cancel. And of course, du's canceling gives you left side equals right side. dy dx. So Leibniz came up with that notation for the chain rule. And specifically, if we were to apply the chain rule to power functions, what would the power rule look like if we were doing a u, which was a composed function, as opposed to just f of x? If we're doing the derivative of u to the n, some function to the n, and by that we mean, let's say, 2x plus 3 to the 7th power, something like that, where it isn't just x to the 7th, it's some function to the 7th. Well, guess what? You can still do the derivative as usual. If you have u to the 7th, let your u be 2x plus 3. The derivative is quite simple. It's nu to the n minus 1. So whatever power you have, and then one less. Exactly what you used to do. The only difference is there's one more step. You must follow it with the derivative of u with respect to x. We always want to get down to x itself. So in this question right here, if this was your y, the derivative would be in two parts. The 7, 2x plus 3 to the 6th, would just be the first part. That is your nu n minus 1. you must follow it with the derivative of the bracketed expression, which is your u. So what's the derivative of 2x plus 3? 2. The result for y prime would be 14 2x plus 3 to the 6. So that's a good illustration of how you do the power rule with a u function. Okay? And you know what, class? Believe it or not, that's what you had over here. Your power was 1/2, wasn't it? And you had an inside function. You had a u function, very simple, of 2x. Okay, so armed with our new definition, we can take a look at this one. And I'll just do it over here, so it will be recorded. What would be the derivative for this particular function? Y prime equals 1/2 2x to the -1/2. But that's incomplete. That's what it would be if you had x in the brackets. But we have 2x in the brackets, so now I have to follow it with the derivative of 2x. What's that? 2. And it nicely cancels the half here, doesn't it? So we're just left with the 1 over root 2x as a result, which was our scissors alternative. Okay. And that was the first page of our notes. And we're going to take a look now at doing a few power function types. Okay. So in number 1, we do have a power function with a chain rule. We have x squared plus 2 all being cubed. So in this case, our u is x squared plus 2. That's our inner function. All right. Now you watched how I did the last couple of examples. Can you write out what you think the derivative of this expression would be? I need everyone on task. All right, so write out the derivative as you think it should be. So you can, in your mind, you can sort of picture this as y equals u cubed, right? U cubed. So what's the derivative of u cubed? Do that first, and then follow it with the derivative of u. Okay, so let's see how you did. Now, we haven't simplified it yet, but how many like my first step? Okay, it is correct. Don't forget, when you do the derivative of x squared plus 2, the derivative of x squared is 2x, and the derivative of plus 2 is just 0, right? So it's just a 2x there. There isn't much simplification to do here. We would simply have 6x, x squared plus 2, quantity squared. Well, I hope you can see that that's a pretty simple example. We can certainly make them more complex when we want to. Number 2, we're baby stepping our way into a little bit more of a complex situation. Okay. Now, in this particular case, I could write it like this. So once again, I'm using a strategy that I learned a couple of lessons ago, where if they give me a function with radicals, I write the powers instead. Okay, so I need a half power inside, and I need a half power outside. Can anyone tell us what our u would be this time? What's our u? X plus x to the half is our u. All right? So give that one a try, using that x plus x to the half as u. I want everyone doing it. If you can't do it, then just raise your hand. I'll come and help you. but I want to see everybody on task here today. Okay, once again, we haven't simplified yet, but do you like my first step? Is everyone good with that? How many would agree with this first step? Can I see your hands? Did I lose anybody here? Okay. All right, so let's just simplify this as much as we can. What will go into the denominator? The 2 will, right? See that 1/2 in there? That 2 can be written in the denominator. What else would be in the denominator? Yeah, the -1/2 power will bring this one downstairs. And of course, we're writing it back with its radical form, right? So instead of the 1/2 power of the whole thing, I'm now writing it as square root down there. And instead of my little x to the 1/2 right there, I'm writing root x. Could you write the numerator in for me, please? All right, so you're probably wondering how much simplification is usually expected in a question like this. Usually we don't want to leave any complex fractions, all right? So in here, I have a fraction in my numerator. I usually don't want to leave it like that, okay? So I'm going to try to give you a sense of when simplification is required and when it's not. And it's a little bit tricky in Math 31 to sometimes understand that. But just so you know, that we don't normally want to leave it like this, not with a fraction in our numerator like this. We would rather bring these two guys together with a common denominator and then bring in that big denominator as a divided fraction. All right, so I'm going to do that. First of all, how can I write 1? Well, in order to match my denominator here, I can write 1 as 2 root x over 2 root x. That's the nice thing about having the number 1 in a fraction question. You can produce any denominator you want very easily, just write the same thing on the numerator. Okay? So what am I going to get in the numerator here? I'm going to get root 2 root x plus 1 all over 2 root x. On the bottom, I have 2 square root x plus root x. And you can think of that as over 1. Now, communication and showing your work properly will be extremely important next year for university calculus, okay? So what I suggest is if you have a complex fraction like this, a fraction over a fraction, make sure your middle bar is the longest bar. That way there's no confusion what you have over what. So do you see how that fraction bar and that fraction bar are smaller than this one? So everybody can clearly see I have this fraction over that fraction. And in Math 31, I think we all know that when we're dividing by a fraction, it's the same as multiplying by the reciprocal. So once again, I'm running out of space here, but 2 root x plus 1 all over 2 root x multiplied by the reciprocal Okay, so there's not much you can. Please do not panic. That was a false bell. This is sort of like the Twilight Zone today. Like we came in here at 11:55. Okay. Not much simplification you can do at this point other than just multiply the two denominators together, multiply the two numerators together, and you're home free. All right. In number 3, we're going to do this derivative in 2 ways. One way using the f and g of x definition, which is more streamlined, and the other way using the Leibniz formula. Let's do Leibniz first. Okay, so if I'm doing Leibniz, what I'm going to do is define my u. So I'm going to let u be the internal portion. Right, so 2x squared plus 1. And then, in preparation for writing the Leibniz formula, we will write our du dx. Our du dx is simply 4x. Just take the derivative of that guy. And next door, we'll write our dy du. So for the Leibniz formula, you will need both of these statements. You'll need the du dx, and you'll need the dy du. The dy du is simply 20u19. So you have u to the 20th power. Therefore, the derivative, up here you could also write y in terms of u. I didn't do that part, but y equals u20, u to the 20th. So dy du is simply this. So let me remind you of the formula. Dy dx, what is it equal to? Dy du multiplied by du dx. It's a very simple formula. We have all the parts we need now to substitute into that formula, don't we? So for dy du, I put 20u19. And for du dx, I put 4x. In the next step, I can actually put in what u is. U is 2x squared plus 1 to the 19. All right, so all I do is replace u with what it is equivalent to. And then the last step, a little bit of simplification. We have 80x altogether, 2x squared plus 1 to the 19th power, and there is our answer. Sometimes students don't like the Leibniz method because there's so much writing with it. So we will now illustrate the chain rule composed function method. That formula looks like this. Fog prime of x equals f prime of gx multiplied by gx. I mean, basically it's the same as Leibniz. It's just written differently. All right, so you do the derivative of the composed function, pretending the composed function is just an f of x. Then you follow it with the derivative of the inner part, gx. So it's a bit more streamlined. So let's focus on our function, and we'll write our answer. So this one involves a little bit of mental math. In this method, you just pretend you've got a single expression to the 20th power, like u to the 20th. And you write 20, exactly the same expression, 19. So that's this part of the formula right there. It's like doing Leibniz in your head. Now, we follow that with the derivative of the inner portion. The inner portion is always the g of x. So it's 4x. Keep in mind that the derivative, the plus 1 part, is 0. We simplify it. So there you go. Yeah, most people do end up using that one. With apologies to Mr. Leibniz, wherever he may be. Okay. All right. With the Leibniz definition, a desired substitution, okay, with the Leibniz definition, because there's no bracket with it, it's just dy dx, it may be hard to show what you want substituted into the derivative after you find it. So Leibniz invented this vertical line approach. So if there's a vertical line after your dy dx with a little x equals something down there, that means you will find the derivative as usual and then do the substitution in that order. It's important that you do not do the substitution first. Okay? So derivative, then substitution. All right, so let's try this one together. Using Leibniz, we know what y is, right? And we know what u is. So writing dy dx equals dy du multiplied by du dx, we obtain 2u for the first step. The derivative of u squared is 2u. Yeah, 2u. Right back at you. Okay? Now, over here, the derivative of u with respect to x is 12x cubed. Now, with Leibniz, you always get a combination of two variables, u with x. So it's very important that you now substitute out the u and put it in. So instead of 2u here, write 2 times 3x to the 4th. This is all multiplied by the other derivative. So you can see there that I took out u and replaced u with 3x to the 4th. What is this going to give me? Well, believe it or not, it's a big number. 6 times 12 is 72, x to the 7th power. Once you have it in that form, it's easy to find what the derivative dy dx at x equals 1 would be. All you have to do is put a 1 wherever you see x. So instead of 72x to the 7, 72, 1 to the 7, and of course, 72. Okay. Number 5. Number 5. If you want fog prime of 3, this has already been set up with the second definition, the FOG definition as opposed to the Leibniz. So we'll go with the flow. We're going to do the FOG here. Keep in mind there's 2 parts here. We do F of G of 3. Whoops, not X, it's 3 this time. So that's always our first factor. And what do we follow it with? G prime of 3. All right. Okay. First of all, did they tell us what G of 3 was? Yes. So in the next step, this is 6. Did they tell us what G prime of 3 was? Yes. It's 5. And did they tell us what F prime of 6 was? Yes. It's 8. So a couple of steps there. We needed, first of all, G of 3. G of 3 was 6. Secondly, we needed F of 6, which was 8. And then thirdly, we needed G prime of 3, which was 5. All of them were provided. Okay. We just have 2 more to do, and it looks like we have about 18 minutes, so maybe 17. Okay. We're going to try this one. Now, I want you to have some appreciation here of our new procedure and how powerful it is. The chain rule is very powerful. And the reason I feel that way is that if I didn't have the chain rule, this would be a real terrible question to work out, wouldn't it? I would have to raise that top binomial to the 10th power. And since I haven't taken Math 30-1, okay, I've taken it. You haven't taken Math 30-1 in its fullness yet. The Pascal's triangle would have to be used to expand this, and then you'd have to expand your denominator. It would take a long time to do, right? It would take hours. This can be done in just a few heartbeats with the chain rule. So a procedure that might have taken you an hour can now be done in less than a minute. Less than a minute, you say? Well, I'm pretty fast. Although, I should say, I am not as fast. I'm not as fast as your teacher. Yeah, because she used to teach with me at a different school when I was a math department head over there. And one day at lunch hour, we had a calculator clearing contest to see who was the fastest in the school. And all of us knew about this 7-key sequence right here that she has up on the board. We all knew about it, right? So, believe it or not, I was the fastest one there. Like, we held it at noon. We played the theme from The Good, the Bad, the Ugly in the background. We wore cowboy hats. We had holsters, right? We had judges to see who was the fastest. I was beating everybody. And then Mrs. Johnson walked in. She was a little late because she had to put on her costume. But she was there. And wouldn't you know it, she had developed a 6-key sequence, and she beat me by a split second. I never lived it down. So, if you can think of the 6-key sequence, you might be able to take her on. That's right. Yeah. I mean, it's pretty simple when you think of it. Okay. All right. So. Well, practice. Practice. Maybe you'll beat her. Maybe you'll beat her. Okay. But you know, she's just coming back from surgery, so don't challenge her right away, okay? Give her a couple of days. All right. Okay, now class, do not write down what I'm about to write, because there could be a mistake in it. If there is a mistake, I want you to find my mistake. Okay, are you watching? You're my judges. You are my judges. Here I go. I'm going to write 10, big guy. I'm calling this guy big guy. Okay, so 10, big guy, 9. Then I'm going to put a dot and a big bracket. Then I'm going to write 2x, x plus 2, minus x squared plus 1, 1, x plus 2, quantity squared. Now this is not simplified, but is my first step correct? Come on, come on. Okay, in just a few seconds, you, the student, will be voting. You can either vote this in as correct for a first step or not correct. Okay? We're not going to do rock, paper, and scissors. We're going to do fingers. If you think it's correct, raise one finger, but please use your index finger. And if you think it's incorrect, raise two fingers. And may the peace be with you. Okay, ready? 1, 2, 3. I think it's correct. Okay. All right. Why do I think it's correct? Well, this is like my u, right? So I think we're all okay with that part. The derivative of u to the 10th is 10u to the 9th, right? The problem is the derivative of u. Oh, students, this is a great review of the quotient rule, isn't it? How did we do the quotient rule? U is a quotient. How did we do it? Start with the derivative of the top. We always start with the derivative of the top, whether we're doing product or quotient. So f prime comes first, right? What's the derivative of x squared plus 1? 2x. Then you just write down g, x plus 2. The quotient rule has subtract here. Product rule has addition. Quotient rule has subtract. Then the other way around. Just write down f, x squared plus 1, and follow with the derivative of g. What's the derivative of x plus 2? 1. Isn't it beautiful? Yeah. And what did I put it over? Did I put it over a derivative? No. I just put it over g squared. So the quotient rule, always finish it with the bottom function squared. Don't do its derivative there. Half the battle with this one, though, is simplifying it. So fasten your seat belts. We're gonna simplify this one. Okay. I don't know if I'm going to finish today. I'm going to try hard. Okay. Not going to touch the denominator here. How will the numerator simplify? Everybody look at that numerator. It's a short class. It's almost over. We got 9 minutes. Look at the numerator. X squared, correct? Because we have 2x squared, take away 1x squared. And what about the x's? 2x times 2, 4x. And then what? Minus 1. All right. The only other simplification I can do here is I can bring together these two denominators. So I have this. The 9th power distributes to the numerator and the denominator. Allowing us to bring together the two denominators, right? To what power will they be? Yes. If you said 11, you're absolutely right. 11 is your number today. And that's all the simplification that would normally be required here. Okay, you can probably understand why we didn't do a quiz today. Okay. Let's take a look at 7a. Okay. These are actually pretty easy to do. Pretty easy to do. If it was all like 7a, we'd be great. This is a nested function composed of f and x to the 4th. All right, so when we do our derivative, the derivative of f x to the 4th is written down. Since f, now listen, since f is an unknown function, we can't elaborate. All we can write is f prime x to the 4th. Oh, but we do know what the nested function is. We know what our u is, or our g of x. It is x to the 4th. So that derivative we can elaborate. So where we can't, we just leave it. Where we can, we do it. All right? So all you can do here is just write the 4x cubed in front. Not much simplification possible because part of it is unknown. All right, class. In question B, believe it or not, we have a product rule and a nested function and an unknown function, all in one question. All right, so the first thing we're going to do is the product rule. The product rule, you start by taking the derivative of the first function. The derivative of x cubed, very easy. 3x squared. Then we multiply that by the second function as it stands. We don't change it. Then we put a plus sign. We write the first function as it stands. We don't change it. And then for the second function, how would I write its derivative? I just have to write f prime of x squared. But it's nested, so I have to follow it with the derivative of the g of x, 2x. Is there any simplification possible? Well, in the second term, there's a little bit. And you could do some common factoring, but in Math 31, we only do useful common factoring. If we factor something out and it cancels something in the denominator, then yes. But we don't just factor for factor's sake. So we'd leave it just like this. There is no advantage to you to factor out the x squared. Yes? No, because we are doing the product rule. Okay, now, we had a nested function right here, didn't we? So the u function is x squared, so we must, according to the chain rule, multiply by 2x, which is... Yeah, it's a product rule and a chain rule. It's both. Yeah. Okay. Could we have a double nested function? Yes. This is a u inside a g, which is inside an f. Afraid it's going to hurt your brain? And I'd have to send you home brain damaged? Mine's already damaged, so I got to do it. All right. So, okay, it's quite simple, class. Start at the outside and work in. We always start with the outer function. So f prime of g of x cubed. But since there was a nest inside, we now must take the derivative of the inner part. So what's the derivative of g? Well, we don't know what it is, so g x cubed. But is there a nest inside? Yes. Do we know what the nest is this time? Yes. So this time we do the derivative of the inner part, and we can write a function. 3x squared. So the only thing you could do here is just put the 3x squared in front. I don't think there's any other simplification because two of the functions are unknown functions. We don't know what they are. And Mr. Ashton is thinking, is there enough time for D? How many want me to do D? Okay. Yeah, it's quick. Yeah, it's really quick. Fast as I can? All right. Here it is. G. Okay, sorry. Started. I got too excited. Okay. Start with the top. Take its derivative. That's the derivative of the top. Multiply it by the bottom as it stands. Don't do the derivative. Subtract. Multiply by the top as it stands. Don't do the derivative. And now do the derivative of the bottom. G prime of 4x multiplied by 4. Because it's 4x in the brackets. And at the bottom, g of 4x would be quantity squared. Did it hurt your brain? Yeah, a little bit. Yeah. Okay. You know what hurts my brain sometimes? Talking too much. Oh, that went on there. Sorry. Can you delete that last one? Okay. Sorry. All right. Oh, let's stop it. Okay. Stop.